So that's a good time to go back to our analysis. So let's actually study how the approximation error, which we know is there in all the three cases, affect the solution. Okay, how do you do that? So from the study we did on the heat equation, what's the best way to analyze how the approximation error gets translated into the solution? Yes?
Studying how the approximation error evolves with the type.
Yeah, studying how the approximation error evolves, and that's the error equation. So the error equation is an equation satisfied by, well, the solution error, right? So the error is defined as the numerical solution minus the analytical solution. So that's, if we can derive an equation satisfied by this error, we are going to know how the error is going to change and evolve. And this is what's different between these three cases. Okay, so if the error is like this, then of course the error at a grid point I is basically Wi minus W. I'll just write W superscript A at I delta X, right? Okay, and if you look at the derivative, time derivative of EI, we have the time derivative of Wi dt minus, well, what's the derivative of WA? It's basically partial WA partial T at X equal to I delta X, right? The partial derivative means the derivative of the function when you are fixing X. So this is basically the ddt of this quantity. So now we can plug in respective the finite difference differential operator and the analytical analytical operator, right? So we know this. We know that the numerical solution satisfy dwi dt equal to minus u of, well, three cases, either wi plus 1 minus wi delta x, or wi minus wi minus 1 over delta x, or the average of them, right? While partial wa partial t actually satisfy minus u times partial w partial x. So basically, if I plug both of these into into the error equation we are deriving, what we get is minus u is pulled out of either wi plus wi plus 1 minus wi over delta x times the derivative, or the backward difference. So all of these are basically the truncation error, right? So what I write is u times tau. All right, so this is well, is it the case? So is this going to be useful? Yes? Okay, so what we defined the tau. So okay, so here what I did is I made a classical mistake in the analysis of how the error evolves. Okay, is that I was looking at the difference between a numerical differential operator and analytical differential operator on two different functions. the numerical differential operator is on W, so it's on the numerical solution, while the analytical derivative is on the analytical solution. And as we can see from, for example, here, the numerical solution and analytical solution, are they the same? No, right? Numerical solution is 85 orders of magnitude larger. So if I take the numerical derivative on the function that is 10 to the 85, while I'm taking the derivative of the analytical solution, which is on the order 1, is that the truncation error or not? What is the truncation error? Right? Do we see? Does everybody see what the mistake is? The truncation error. So this is not equal to truncation error. The truncation error is defined as if I take the same function, wi plus 1 minus wi over delta x minus the derivative of the same function, right? If I put an analytical solution here, while numerical solution here, this is not the truncation error. So this is actually not true. Okay, do we all see that? So instead, what should I do? Yes, I can do that at the initial condition, but then this equation is only going to be valid for at t equal to 0, right? So I cannot predict what the solution is going to be. For example, how much error I would have at t equal to 1. All right, I can. If I write this, I can only predict how the error is at t equal to epsilon, which is not that useful. So how do we fix that? Yes? Well, the way we fix this is that we know E, right? E is actually the difference between numerical and analytical solutions. Okay? So instead of just going directly to here, we actually use the E itself. All right. So the way we use E itself is that we are going to write dwi dt as what? As well, we don't, let's wait 1 second. We don't start from here. We are going to be starting from here. We are going to be starting saying wi plus 1 minus wi over delta x is actually equal to wi plus 1 is equal to w analytical I plus 1 plus E at I plus 1, right? And wi is equal to wi analytical minus EI. And this over delta x. So why am I doing this? Because this actually gets the numerical operator operated on the analytical solution, plus another term that is actually the same differential operator operated on the error. Okay, yes?
Why is that against the spatial coordinate instead of time?
Why am I doing this for the spatial coordinate, not the time? Because I want to actually get to the truncation error, right? The truncation error is defined as the difference between the spatial differential operators.
But that error time isn't error against time, dEI over dt.
Yes, we want to basically write the evolution of the error as time evolves as a function of the truncation error, as a function of tau. Right, so the goal of this is to then we are going to be plugging this into the right hand side of what we have already derived. Then we get dI dt is going to be minus u times this guy minus the analytical derivative, right? So we are going to have these plus these minus the analytical derivative for I equal to x equal to I delta x. Okay, so this and this together is the truncation error. Now I'm applying different differential operators, analytical and numerical, to the same function. Okay, so now I write it as minus u times the numerical differential operator operated on the error plus tau. Okay, does it make sense?